Welcome to What is a Control System class at Triune Biblical University Global Extension, USA. Today we're diving into the world of control systems, a fundamental concept in engineering that shapes how machines, devices, and even everyday appliances behave. Whether you realize it or not, control systems are all around us, quietly ensuring that everything from your home heating to your car's cruise control works just as you expect. In this session, we'll explore what a control system actually is, why it's so important, and the foundational objectives that guide its design. Let's start by understanding the basic definition and purpose of a control system. Control system is essentially a setup designed to regulate the behavior of another system to achieve a specific desired output. Think of it as a manager that constantly checks and adjusts how things are running to keep everything on track. In technical terms, it's a system that takes inputs, processes them, and produces outputs that guide the main system's behavior. This definition forms the backbone of countless engineering applications, from industrial machines to household gadgets. Simply, a control system ensures that a system behaves the way we want it to. Imagine you want your room to stay at a comfortable temperature or your car to maintain a steady speed. The control system is the invisible hand making sure things don't go off course. It's about making sure the actual outcome matches what you intended, even when things change or unexpected disturbances occur. Let's look at some everyday examples. Think about your home's heating system, which keeps your room at the temperature you set, or consider how your car's cruise control maintains a constant speed on the highway. Even a robot arm in a factory uses a control system to move precisely to the right position. These examples show how control systems are woven into the fabric of modern life, quietly working behind the scenes. Control systems are crucial in engineering because they help maintain stability, reduce errors, and ensure that systems respond appropriately to changes. Without them, machines and devices would be unreliable, unpredictable, and even unsafe. Imagine a robot that can't stay on course or a vehicle that wobbles uncontrollably. These are the kinds of problems control systems are designed to prevent. Main objectives of any control system are stability, accuracy, and responsiveness. Stability means the system doesn't go out of control. Accuracy ensures the output matches the desired value as closely as possible. Responsiveness is about how quickly the system reacts to changes or disturbances. These objectives guide engineers when designing and tuning control systems for all sorts of application. Stability is perhaps the most critical objective. A stable control system keeps the output from spiraling out of control even when faced with disturbances. For example, if a gust of wind hits a drone, a stable control system will quickly bring it back to its intended flight path. Without stability, systems can become dangerous or unusable. Accuracy is all about how closely the system's output matches the desired value. For instance, if you set your thermostat to 22 degrees C, accuracy means the room temperature stays as close to 22 degrees C as possible. High accuracy is essential in applications like manufacturing, where even small errors can lead to defects or wasted resources. Responsiveness refers to how quickly a control system reacts to changes or disturbances. Imagine driving a car and suddenly needing to slow down. Your car's control system must respond instantly to your input. Fast responsiveness is vital in safety-critical systems like vehicles and aircraft, where delays can have serious consequences. Without control systems, many engineered systems would simply not function as intended. Robots would drift off course, vehicles could become unstable, and aircraft might be unsafe to fly. Control systems are the invisible force that keeps everything running smoothly, reliably, and safely, even when the environment changes or unexpected events occur. One of the most important roles of a control system is to maintain stability. This means keeping the system's output within safe and predictable limits, even when faced with disturbances or changes in the environment. For example, a drone's flight controller constantly adjusts its motors to keep it level, even if the wind picks up. Reducing error is another key objective. Control systems constantly compare the actual output to the desired output and make adjustments to minimize any difference. This process is what allows machines to perform tasks with high precision, whether it's a robotic arm assembling electronics or a car maintaining a set speed. Disturbances are unexpected changes that can throw a system off course. A good control system detects these disturbances and reacts quickly to bring the system back to its desired state. For example, if a sudden load is placed on an elevator, the control system adjusts the motor to maintain smooth movement. A reference command is the target value or goal the system should achieve. Control systems are designed to follow these commands as closely as possible. For example, when you set a speed on your car's cruise control, the system works to keep the car moving at that exact speed, adjusting for hills or wind as needed. If control systems didn't exist, engineered systems would be unreliable and potentially dangerous. Robots might drift away from their intended paths, vehicles could become unstable, and aircraft would be unsafe to operate. Control systems are essential for ensuring that technology works as intended, safely and reliably. Imagine a robot without a control system. It would have no way to correct its movements or stay on track. This could lead to errors, collisions, or even accidents in environments like factories or warehouses. Control systems give robots the ability to operate safely and efficiently. Vehicles rely heavily on control systems for stability and safety. Without them, cars could swerve uncontrollably and airplanes might not be able to maintain steady flight. Control systems constantly monitor and adjust the vehicle's behavior to keep it safe and predictable. Aircraft are a prime example of why control systems are essential. Modern planes use sophisticated control systems to maintain altitude, adjust for turbulence, and ensure a smooth flight. Without these systems, flying would be far more dangerous and less comfortable. Let's break down a common example: a home thermostat system. The thermostat lets you set your desired temperature, which becomes the reference for the system. The heater acts as the actuator, the room is the plant, and the thermometer is the sensor. The control system works by continuously measuring the room temperature and adjusting the heater to maintain your set point. In the thermostat example, the desired temperature you set is called the reference. The control system's job is to keep the actual room temperature as close to this reference as possible, making adjustments whenever there's a difference. This is a simple but powerful illustration of how control systems work in practice. The heater in your thermostat system is known as the actuator. It's the part of the system that actually makes changes to the environment, in this case, by adding heat to the room. The control system tells the actuator when to turn on or off based on the sensor's readings. In control system terminology, the room being heated is called the plant. The plant is the part of the system whose behavior we want to control. The control system's goal is to keep the plant's output, in this case the room temperature, at the desired value. The thermometer acts as the sensor in the thermostat system. Its job is to measure the current room temperature and send this information to the control system. Accurate sensing is crucial for the system to make the right adjustments and maintain comfort. A key feature of control systems is their ability to continuously adjust. In the thermostat example, the system is always checking the temperature and making small changes to the heater's operation. This ongoing process ensures that the room stays as close as possible to your desired comfort level. The thermostat system is a classic example of feedback in action. The system measures the current state, compares it to the reference, and makes adjustments to minimize any difference. This feedback loop is at the heart of most control systems, enabling them to adapt and maintain performance. Feedback allows control systems to correct errors and respond to changes. Without feedback, the system would have no way of knowing if it's on track or if adjustments are needed. This is why feedback is a foundational concept in control engineering. Not all control systems are designed the same way. Some use feedback to adjust their behavior. These are called closed-loop systems. Others operate without feedback, simply following a set of instructions. These are open-loop systems. Understanding the difference is key to mastering control system design. An open-loop system operates without feedback. It follows a predetermined set of instructions regardless of the actual outcome. For example, a basic washing machine runs through its cycle without checking if the clothes are clean. Open-loop systems are simple but can't correct for errors or disturbances. Closed-loop systems use feedback to monitor and adjust their behavior. The thermostat system is a perfect example. It constantly checks the room temperature and adjusts the heater as needed. Closed-loop systems are more complex but offer greater accuracy and adaptability. The main difference between open-loop and closed-loop systems is feedback. Open-loop systems are straightforward but limited, while closed-loop systems are more flexible and reliable. Engineers choose the right type based on the application's needs for accuracy, stability, and responsiveness. To sum up, control systems are essential for ensuring that machines and devices behave as intended. They maintain stability, improve accuracy, and respond to changes, making technology safer and more reliable. Whether it's your home thermostat or a complex aircraft, control systems are the foundation of modern engineering. Remember, a control system is all about regulation and adjustment. Its main objectives, stability, accuracy, and responsiveness, guide how engineers design and tune these systems. Understanding these basics is the first step toward mastering more advanced control concepts. Control systems aren't just for engineers, they impact our daily lives in countless ways. From keeping our homes comfortable to making transportation safer, these systems are everywhere. Recognizing their presence helps us appreciate the technology we often take for granted. From an engineering perspective, control systems are a core discipline. They require a blend of theory, practical design, and problem-solving skills. Engineers must understand how to model systems, design controllers, and ensure that everything works together seamlessly. Every control system is made up of key components: the reference, actuator, plant, and sensor. Each plays a vital role in ensuring the system works as intended. Understanding these components is crucial for anyone studying or working with control systems. The reference sets the goal for the control system. It's the target value the system should achieve, like the temperature you set on your thermostat or the speed you want your car to maintain. The entire system works to keep the output as close to this reference as possible. The actuator is the part of the system that makes changes to the environment. It receives commands from the control system and acts accordingly, whether it's turning on a heater, adjusting a motor, or opening a valve. Actuators are essential for translating control decisions into real-world actions. The plant is the part of the system being controlled. It could be a room, a vehicle, a robot arm, or any other process. The control system's job is to keep the plant's output at the desired level despite disturbances or changes in the environment. Sensors are the eyes and ears of a control system. They measure the actual output and provide feedback to the controller. Accurate sensing is vital for the system to make the right adjustments and maintain performance. The controller is the brain of the control system. It receives information from the sensor, compares it to the reference, and decides what action the actuator should take. The controller's logic and algorithms are what make the system intelligent and adaptive. When all these components, reference, actuator, plant, sensor, and controller, work together, you have a complete control system. Each part plays a unique role, and their interaction is what allows the system to achieve its objectives. This teamwork is what makes control systems so powerful and versatile. Modern technology relies on control systems more than ever. From smart homes to autonomous vehicles, these systems are at the heart of innovation. As technology advances, the role of control systems will only grow, making them an exciting field to study and work in. Studying control systems opens up a world of possibilities. Whether you're interested in robotics, aerospace, manufacturing, or smart devices, understanding control is a valuable skill. This foundational knowledge will serve as a stepping stone to more advanced topics in engineering. Now that you understand the basics of control systems, you're ready to explore more advanced concepts. In future lessons, we'll dive deeper into different types of control systems, how they're designed, and the mathematics behind them. This journey will build on the solid foundation you've gained today. In conclusion, control systems are the unsung heroes of modern engineering. They ensure that machines, devices, and processes work reliably, safely, and efficiently. By mastering the foundations of control systems, you're taking the first step toward understanding and shaping the technology of tomorrow.
Welcome. Today we're diving into the fascinating world of control systems, focusing on the differences between open-loop and closed-loop systems. Whether you realize it or not, control systems are everywhere, from your home appliances to advanced robotics. By the end of this video, you'll be able to distinguish between open-loop and closed-loop systems, understand the concept of feedback, and recognize the strengths and weaknesses of each approach. Let's get started by exploring what makes a control system tick, and why understanding these concepts is so important in engineering and everyday life. Let's begin with open-loop systems. An open-loop control system is one that operates without any feedback. In other words, it doesn't measure its output or make any corrections based on what actually happens. The system simply follows a set of instructions, regardless of the outcome. This makes open-loop systems straightforward and easy to design, but it also means they can't adapt if something goes wrong. Think of it as setting a timer and walking away. The system will do exactly what you told it, no more, no less. Open-loop systems have several defining characteristics. First, they do not measure the output, so there's no way to know if the desired result was achieved. Second, there's no correction mechanism. If something goes wrong, the system won't notice or fix it. Third, the design is usually simple, which keeps costs low and makes the system easy to implement. However, this simplicity comes at a price, especially when conditions change or disturbances occur. Classic example of an open-loop system is a washing machine that runs on a timer. You set the wash cycle for a fixed amount of time, and the machine completes the process regardless of how clean the clothes actually are. There's no sensor to check if the dirt is gone or if more washing is needed. The machine simply follows the preset instructions, making it a perfect illustration of open-loop control. Another everyday example is a fixed-time traffic light. The light changes at regular intervals, regardless of the actual traffic conditions. It doesn't sense whether cars are waiting or the road is empty. This makes the system simple and predictable, but it can also lead to inefficiencies, like waiting at a red light when no cars are coming from the other direction. Open-loop systems have some clear advantages. Their simplicity means they are easy to design and implement. They also tend to be less expensive, since they don't require sensors or complex controllers. For tasks where precision isn't critical, or where the environment is predictable, open-loop systems can be a great choice. However, it's important to remember that these benefits come with certain trade-offs. Despite their simplicity, open-loop systems have significant limitations. Since they don't measure output, they can't correct errors or adapt to changes. This makes them sensitive to disturbances. If something unexpected happens, the system can't respond. For example, if the water pressure drops during a washing cycle, the machine won't adjust, and your clothes might not get clean. These drawbacks limit where open-loop systems can be effectively used. Now that we've covered open-loop systems, let's move on to closed-loop systems. These systems are designed to overcome many of the limitations we just discussed. The key difference: closed-loop systems use feedback to monitor and adjust their output, making them much more adaptable and accurate. Let's see how this works in practice. Closed-loop control system is one that uses feedback to compare the actual output with the desired output. If there's a difference, called an error, the system automatically makes adjustments to minimize that error. This feedback loop allows the system to respond to changes and disturbances, maintaining performance even in unpredictable environments. Closed-loop systems are found in everything from household thermostats to advanced robotics. Feedback is the heart of any closed-loop system. It involves measuring the system's output and comparing it to the target value. If the output doesn't match what's desired, the system takes corrective action. This continuous process of monitoring and adjusting is what gives closed-loop systems their accuracy and reliability. Feedback enables the system to learn from its performance and make real-time improvements. A great example of a closed-loop system is cruise control in a car. When you set your desired speed, the system constantly measures the actual speed and compares it to your setting. If the car slows down going uphill, the system detects the error and increases the throttle to maintain the set speed. This automatic adjustment is only possible because of the feedback loop. Another example is a robot arm used in manufacturing. The arm is programmed to move to a specific position. Sensors measure the actual position and send this information back to the controller. If the arm is off target, the controller makes adjustments until the desired position is reached. This precise control is essential for tasks that require accuracy and consistency. Aircraft autopilot systems are another powerful example of closed-loop control. The autopilot constantly monitors the plane's position, speed, and altitude, comparing them to the desired flight path. If there's any deviation, the system makes real-time adjustments to keep the aircraft on course. This level of control is only possible with continuous feedback. Closed-loop systems offer several important benefits. They provide improved accuracy, since the system can correct its own errors. They're also better at rejecting disturbances. If something unexpected happens, the system can adapt. Finally, closed-loop systems help maintain stability, ensuring consistent performance even when conditions change. These advantages make closed-loop control essential in many modern applications. Closed-loop systems are powerful. They also come with some challenges. They are typically more complex and expensive than open-loop systems, since they require sensors, controllers, and sometimes advanced software. Designing and maintaining these systems can be more demanding. However, for applications where precision and adaptability are critical, these extra costs are often justified. Let's compare open-loop and closed-loop systems side by side. Open-loop systems are simple and inexpensive, but they can't adapt to changes or correct errors. Closed-loop systems, on the other hand, use feedback to maintain accuracy and stability, but they require more components and are more costly. The choice between the two depends on the specific needs of the application. Feedback is the process of using output information to influence future actions. In closed-loop systems, feedback is what allows the system to compare actual performance with the desired outcome and make corrections. This concept is central to modern control theory and is used in countless applications, from industrial automation to everyday gadgets. In control systems, error is defined as the difference between the desired output and the actual output. The controller's job is to minimize this error as much as possible. By constantly measuring and adjusting, closed-loop systems can keep the error small, ensuring that the system performs as intended. Controllers are the brains of closed-loop systems. They receive information about the system's output, compare it to the desired value, and decide what actions to take. This might involve increasing power, changing direction, or making other adjustments. The controller's ability to respond quickly and accurately is what makes closed-loop control so effective. Every control system, whether open or closed-loop, is made up of several key components. These typically include an input or reference signal, a controller and actuator, and the process or plant being controlled. In closed-loop systems, sensors and feedback paths are also essential. Understanding these components is crucial for designing effective control systems. The input or reference signal represents the desired outcome for the system. In a washing machine, this might be the selected wash cycle. In cruise control, it's the speed you set. The system's job is to achieve this target as closely as possible, using either open-loop or closed-loop control strategies. Actuators are devices that carry out the controller's commands. They convert electrical signals into physical actions, such as turning a motor, opening a valve, or moving a robotic arm. Actuators are essential for translating control decisions into real-world effects, making them a key part of any control system. Sensors play a critical role in closed-loop systems. They measure the actual output of the system and send this information back to the controller. Without sensors, feedback wouldn't be possible, and the system couldn't adapt to changes or correct errors. Sensors can measure a wide range of variables, from temperature and speed to position and pressure. Feedback pathway is the route by which information about the system's output is returned to the controller. This pathway can be electrical, mechanical, or even digital, depending on the system. The quality and speed of feedback are crucial for the system's performance, especially in applications that require rapid response. Disturbances are unexpected changes that can affect a system's performance. In open-loop systems, disturbances can cause significant errors, since there's no way to detect or correct them. Closed-loop systems, however, can sense disturbances through feedback and make adjustments to maintain the desired output. Stability refers to a system's ability to maintain controlled behavior over time. Closed-loop systems are generally more stable because they can correct deviations from the desired output. Open-loop systems, lacking feedback, are more likely to drift or become unstable if conditions change. Accuracy is how closely a system's output matches the desired value. Closed-loop systems excel in accuracy because they constantly correct errors. Precision, on the other hand, refers to the consistency of the output. Both are important, but feedback is especially critical for achieving high accuracy in dynamic environments. Cost is a major factor when choosing between open-loop and closed-loop systems. Open-loop systems are usually less expensive, since they don't require sensors or complex controllers. Closed-loop systems cost more but offer greater performance and adaptability. The right choice depends on the application's requirements and budget. Open-loop systems are best suited for applications where the environment is predictable and precision is not critical. Examples include simple timers, basic lighting controls, and other tasks where the outcome is unlikely to be affected by disturbances. Their simplicity and low cost make them ideal for these situations. Closed-loop systems are the go-to choice for applications that require high accuracy, adaptability, and stability. They're essential in environments where conditions can change rapidly or where precision is vital, such as in robotics, automotive systems, and industrial automation. The investment in sensors and controllers pays off through improved performance. Home thermostat is a classic closed-loop system. You set the desired temperature, and the thermostat measures the actual room temperature. If the room is too cold, it turns on the heater. If it's too warm, it turns it off. This constant adjustment keeps your home comfortable, regardless of changes outside. Basic toaster is an open-loop system. You set the timer, and the toaster runs for that amount of time, regardless of how brown the bread actually gets. There's no feedback to check if the toast is done to your liking, which can lead to inconsistent results. Smart oven, on the other hand, uses sensors to monitor the internal temperature and adjust cooking time automatically. This closed-loop approach ensures your food is cooked perfectly every time, adapting to changes in the oven or the food itself. In industrial settings, open-loop systems are often used for simple, repetitive tasks where conditions are stable. For example, a conveyor belt that runs for a set time to move products from one station to another. These systems are cost-effective and reliable when the process doesn't require adaptation. Closed-loop systems are widely used in industrial automation, where precision and adaptability are crucial. For example, robotic assembly lines use sensors and feedback to ensure each part is placed accurately, even if conditions change. This level of control is essential for maintaining quality and efficiency. Recap: open-loop systems operate without feedback and are best for simple, stable tasks. Closed-loop systems use feedback to monitor and adjust their output, making them ideal for complex or changing environments. Understanding these differences helps engineers choose the right approach for each application. Feedback is what sets closed-loop systems apart. It allows for continuous improvement and adaptation, making systems more reliable and effective. As technology advances, feedback control is becoming more common in everything from consumer electronics to large-scale industrial processes. Selecting between open-loop and closed-loop control depends on the specific needs of your application. Consider factors like required accuracy, cost, complexity, and the likelihood of disturbances. In many cases, a combination of both approaches can offer the best balance of performance and efficiency. Modern control systems are increasingly integrating advanced sensors, artificial intelligence, and network connectivity. These innovations are making closed-loop systems even more powerful, enabling smarter automation and greater adaptability. Staying updated with these trends is key for anyone working in engineering or technology. It's a common misconception that closed-loop systems are always better. In reality, the best system depends on the application. Sometimes, the simplicity and reliability of open-loop control are exactly what's needed. Understanding the strengths and limitations of each approach is essential for making informed decisions. The future of control systems lies in greater integration, intelligence, and connectivity. As systems become more complex, the ability to monitor, adapt, and optimize in real time will be increasingly important. Both open-loop and closed-loop systems will continue to play vital roles, often working together in hybrid configurations. Let's review the key points. Open-loop systems are simple and cost-effective, but lack adaptability. Closed-loop systems use feedback to achieve high accuracy and stability, but they're more complex and expensive. The choice depends on the specific requirements of your application. Understanding both types is essential for effective system design. Control systems are everywhere, from household appliances to industrial robots. Understanding how open-loop and closed-loop systems work helps you appreciate the technology behind everyday devices and prepares you for more advanced study or professional work in engineering. In summary, both open-loop and closed-loop control systems have their place in modern technology. By understanding their differences, advantages, and limitations, you can make better decisions in design and application. Feedback is the key to adaptability and precision, but simplicity and cost are also important considerations. As you continue your studies, keep an eye out for control systems in the world around you. Notice how feedback is used to improve performance and how different systems are designed to meet specific needs. This foundational knowledge will serve you well in future engineering courses and real-world problem solving.
Welcome. Today we'll explore the essential components that make up a control system. Whether you're interested in robotics, automation, or engineering, understanding these building blocks is crucial. Control systems are everywhere, from the thermostat in your home to advanced robotic arms in factories. In this session, we'll break down each component, see how they interact, and relate them to real-world robotics examples. By the end, you'll have a clear picture of how control systems work and why each part is important. Let's get started by identifying the key components that form the backbone of any control system. Every control system, no matter how simple or complex, is built from a few major components. These include sensors, controllers, actuators, and the plant. Each plays a unique role in ensuring the system operates as intended. Think of them as the senses, brain, muscles, and body of a robot. Sensors gather information, controllers make decisions, actuators carry out actions, and the plant is the system being controlled. Understanding how these parts fit together is the first step to mastering control systems. Start with sensors. Sensors are like the eyes and ears of a control system. They measure the output of the system and provide real-time data. For example, a temperature sensor can monitor heat levels, an encoder can track position, and a gyroscope can sense orientation. Without sensors, the system would have no way of knowing what's happening, making it impossible to adjust or correct its actions. In robotics, sensors are critical for feedback and precise control. Sensors come in many forms, each suited for specific tasks. Temperature sensors detect heat, encoders measure rotation or position, and gyroscopes sense angular movement. In robotics, you might find all three working together. For instance, a robot arm uses encoders to know its position, gyroscopes to maintain balance, and temperature sensors to prevent overheating. The choice of sensor depends on what needs to be measured and how precise the information must be. Next, we have the controller. Think of the controller as the brain of the control system. It receives information from the sensors, compares it to the desired outcome, and decides what needs to be done. The controller processes errors, differences between what's happening and what should happen, and determines the corrective action. Controllers can be analog, digital, or microcontroller based, each offering different levels of complexity and flexibility. Controllers come in several forms. Analog controllers use continuous signals, digital controllers operate with discrete signals, and microcontroller-based systems use programmable chips. In robotics, microcontrollers are popular because they can be programmed for complex tasks and easily integrated with sensors and actuators. The choice of controller affects how quickly and accurately the system can respond to changes. Actuators are the muscles of a control system. They take the control signals from the controller and convert them into physical actions. For example, a motor spins a wheel, a hydraulic piston moves a part, and a servo positions a robotic arm. Without actuators, the system couldn't interact with the physical world. In robotics, actuators are essential for movement, manipulation, and performing tasks. There are many types of actuators, each designed for specific tasks. Motors are common in robots for spinning wheels or moving arms. Hydraulic pistons provide powerful linear motion, often used in heavy machinery. Servos offer precise control, making them ideal for tasks like positioning a robotic arm. The choice of actuator depends on the required movement, force, and precision. Plant is the part of the system being controlled. In robotics, the plant could be a robot arm, a vehicle engine, or even a drone. The plant receives actions from the actuator and responds accordingly. It's the main focus of the control system, as all other components work together to ensure the plant behaves as desired. Understanding the plant's characteristics is vital for designing effective control systems. Let's look at some examples of plants in control systems. A robot arm is a classic example where precise movement is needed. In vehicles, the engine is the plant with controllers managing speed and efficiency. Drones are another example where the plant includes motors, propellers, and sensors working together. Each plant has unique characteristics that influence how the control system is designed. Now that we've introduced each component, let's see how they work together. The magic of a control system lies in the interaction between sensors, controllers, actuators, and the plant. Each part communicates with the others, forming a continuous loop. This loop ensures the system can respond to changes and maintain desired performance, even in the face of disturbances. Key feature of most control systems is the feedback loop. Here, how it works: a reference value is set, such as a desired position or speed. The system compares its current state to this reference. The controller processes any error and sends a signal to the actuator, which adjusts the plant. The sensor then measures the new output and the loop continues. This process allows the system to self-correct and achieve its goal. Reference value is the target or desired outcome for the system. For example, you might want a robot arm to move to a specific angle or a vehicle to maintain a certain speed. The reference value guides the entire control process, providing a benchmark for the controller to compare against. Setting the right reference is crucial for achieving the desired system behavior. Once the reference value is set, the system compares the current output to this target. The difference between the two is called the error. This error tells the controller how far off the system is from the goal. By continuously measuring and minimizing this error, the control system can adjust its actions and maintain accuracy. The controller takes the error and decides what corrective action to take. It processes the information, determines the best response, and sends a control signal to the actuator. The controller's job is to keep the system as close to the reference value as possible, even when conditions change or disturbances occur. When the actuator receives the control signal, it creates a physical change in the plant. This could mean moving a robotic arm, adjusting a valve, or changing the speed of a motor. The actuator's response is what allows the system to interact with the real world and achieve its goals. After the actuator makes a change, the sensor measures the new output of the plant. This feedback is sent back to the controller, closing the loop. The system can now see how effective its actions were and make further adjustments if needed. This continuous feedback is what makes control systems robust and reliable. Let's walk through a practical example in robotics. Suppose you want a robotic arm to move to a 45-degree angle. The reference value is set to 45 degrees. The sensor detects the arm is currently at 40 degrees. The controller calculates the error 5 degrees and sends a signal to the actuator. The actuator moves the arm and the sensor keeps checking the angle until it reaches the target. This process happens quickly and continuously, ensuring precise movement. Feedback is what sets control systems apart from open-loop systems. With feedback, the system can detect errors and correct them in real time. This makes the system more accurate, stable, and adaptable to changes. In robotics, feedback is essential for tasks that require precision, such as picking up objects or navigating complex environments. It's important to distinguish between open-loop and closed-loop control systems. Open-loop systems act without feedback; they don't check if the desired outcome is achieved. Closed-loop systems, on the other hand, use feedback to monitor and adjust their actions. Most modern robotics systems rely on closed-loop control for better performance and reliability. To analyze and design control systems, engineers often use block diagrams. A block diagram is a visual representation that shows how each component interacts. Blocks represent the components: sensor, controller, actuator, and plant, and arrows indicate the flow of information and signals. This makes it easier to understand and troubleshoot complex systems. Block diagrams aren't just for visualization, they're also used for mathematical analysis. Engineers can assign equations to each block, representing how the component processes signals. This allows for precise calculations, simulations, and predictions of system behavior. Mathematical models are essential for designing effective and reliable control systems. In robotics, sensors play a vital role in enabling autonomy and precision. For example, a mobile robot might use distance sensors to avoid obstacles, encoders to track wheel rotation, and cameras to recognize objects. The combination of different sensors allows robots to perceive their environment and make intelligent decisions. Robotic controllers are often programmable and highly adaptable. They can handle complex algorithms, process data from multiple sensors, and coordinate several actuators at once. This flexibility is what makes modern robots capable of performing intricate tasks, from assembling electronics to exploring other planets. Actuators in robotics come in many forms, each suited for specific movements and tasks. Electric motors are common for wheels and arms, while pneumatic or hydraulic actuators provide strong, smooth motion for heavy lifting. Servos offer precise positioning, making them ideal for delicate operations like surgery or assembly. In robotics, the plant is often a complex system made up of multiple parts. For example, a humanoid robot's plant includes its arms, legs, and torso, all of which must be controlled simultaneously. Understanding the dynamics of the plant is key to designing a control system that can handle real-world challenges. Integrating sensors, controllers, actuators, and the plant into a single system requires careful design. Each component must communicate effectively, and the timing of signals is critical. Engineers use software and hardware tools to ensure seamless integration, allowing the control system to function smoothly and reliably. Designing control systems comes with challenges. Noise in sensor data, delays in actuator response, and unexpected disturbances can all affect performance. Engineers must anticipate these issues and design systems that are robust and adaptable. This often involves filtering sensor data, tuning controllers, and testing under various conditions. Consider a drone as a real-world example. The plant is the drone itself, with motors as actuators, gyroscopes and accelerometers as sensors, and a microcontroller as the controller. The system constantly adjusts motor speeds to maintain balance and follow commands, using feedback from the sensors to stay stable in flight. In vehicles, the engine is the plant. Sensors monitor speed, temperature, and emissions. The controller processes this data and adjusts fuel injection or ignition timing. Actuators carry out these adjustments, ensuring the engine runs efficiently and meets performance targets. Before building a control system, engineers often create mathematical models of the plant and other components. These models help predict how the system will behave and identify potential issues. Accurate modeling is essential for designing controllers that can handle real-world complexities. Simulations allow engineers to test control systems in a virtual environment before building physical prototypes. By simulating different scenarios, they can fine-tune controllers, optimize performance, and ensure safety. This step saves time and resources and helps catch problems early. Controller tuning is the process of adjusting parameters to achieve the best performance. This might involve changing gain values, response times, or other settings. Proper tuning ensures the system responds quickly and accurately to changes without overshooting or oscillating. Safety is a top priority in control system design. Engineers add safeguards to prevent accidents, such as emergency stop buttons, limit switches, and software checks. These features protect both the system and its operators, especially in high-risk environments like factories or laboratories. To increase reliability, control systems often include redundant components. For example, a robot might have backup sensors or controllers that take over if the main ones fail. Redundancy ensures the system can continue operating safely even if something goes wrong. Effective communication between components is essential. Control systems use protocols like CAN, I2C, or Ethernet to transmit data quickly and reliably. Choosing the right protocol depends on the system's complexity, speed requirements, and environment. Many control systems include a human-machine interface (HMI), such as a touchscreen or control panel. The HMI allows operators to set reference values, monitor system status, and respond to alerts. A well-designed HMI improves usability and safety. Modern control systems often include data logging features. By recording sensor readings, actuator commands, and system responses, engineers can analyze performance, identify trends, and troubleshoot issues. Data analysis helps improve future designs and maintenance. With advances in connectivity, many control systems can be monitored and controlled remotely. This is especially useful for systems in hazardous or hard-to-reach locations. Remote access allows for real-time adjustments, diagnostics, and updates, improving efficiency and safety. Control systems can be scaled up or down to fit different applications. From small devices like thermostats to large industrial robots, the same basic principles apply. Scalability ensures that control systems can grow with changing needs and technologies. New technologies are shaping the future of control systems. Artificial intelligence, machine learning, and advanced sensors are making systems smarter and more autonomous. These trends are expanding the possibilities for robotics and automation in many fields. While robotics is a major application, control systems are used in many other areas. Examples include climate control in buildings, process automation in factories, and even medical devices. The same core components, sensors, controllers, actuators, and plants are found in all these systems. To recap, every control system is built from four main components: sensors, controllers, actuators, and the plant. These parts work together in a feedback loop to achieve precise and reliable control. Understanding their roles and interactions is the foundation for designing and analyzing control systems in robotics and beyond. In the next session, we'll dive deeper into how engineers represent control systems using block diagrams. This powerful tool helps visualize and analyze complex systems, making it easier to design effective solutions. Stay tuned as we explore block diagram representation and its importance in control engineering. Control systems are at the heart of modern technology, enabling everything from simple appliances to advanced robots. By mastering the components and their interactions, you'll be equipped to tackle real-world engineering challenges. Remember, sensors, controllers, actuators, and the plant form the foundation of every control system. Keep exploring and you'll unlock even greater possibilities in robotics and automation. Welcome to our exploration of block diagram representation and its applications in engineering. Today, we'll break down how these diagrams help us understand complex control systems, identify feedback loops, and connect theory to real-world technology. By the end of this session, you'll be able to interpret basic control system block diagrams, spot feedback mechanisms, and see how these concepts are applied in robotics, automotive, and aerospace fields. Let's start by understanding what a block diagram is and why it's so essential for engineers and problem solvers everywhere. Block diagram is a visual tool that represents the main components of a system and the flow of signals between them. Think of it as a map that simplifies how different parts of a control system interact. Each block stands for a specific component, like a controller or actuator, while arrows show how information or signals move from one part to another. This approach makes it easier to analyze, design, and troubleshoot even the most complex system. Let's look at a classic example, the basic closed-loop control system. In this setup, you start with a reference input which passes through a summing junction. The controller processes the error, sending commands to the actuator. The actuator influences the plant, and the plant produces the output. A sensor measures this output and sends feedback to the summing junction, closing the loop. This feedback is crucial for making real-time adjustments and maintaining system stability. Every block diagram is made up of a few key elements. First, the blocks themselves represent the main components, like controllers, actuators, and sensors. Arrows indicate the direction of signal flow, showing how information travels through the system. The summing junction is where the system calculates the error between the reference and the actual output. These elements work together to create a clear picture of how the system operates. How do engineers use block diagrams? The main reason is to simplify complex systems. By breaking down a system into manageable parts, block diagrams make it easier to model mathematically, analyze stability, and design effective control strategies. They serve as a universal language for engineers, allowing teams to communicate ideas clearly and efficiently, regardless of the system's complexity. Block diagrams aren't just for visualization, they're also powerful tools for mathematical modeling. Each block can represent a mathematical function or equation that describes how that part of the system behaves. By connecting these blocks, engineers can build a complete mathematical model of the system, making it possible to predict performance, optimize design, and ensure reliability. One of the most important uses of block diagrams is in stability analysis. By representing the system's feedback loops and components, engineers can study how the system responds to changes or disturbances. This helps in identifying potential issues before they arise and ensures that the system will remain stable under different operating conditions. Feedback loops are at the heart of many control systems. In a closed-loop system, the output is constantly measured and compared to the reference input. If there's a difference, the system makes adjustments to minimize the error. This continuous process allows the system to adapt to changes and maintain desired performance, which is essential in applications like robotics and automotive controls. It's It's important to distinguish between open-loop and closed-loop systems. Open-loop systems operate without feedback, they simply follow the input commands. Closed-loop systems, on the other hand, use feedback to adjust their behavior and achieve better accuracy and stability. Most modern engineering applications rely on closed-loop systems for their superior performance. Let's see how block diagrams are used in robotics. For example, in joint angle control, each joint's position is measured by a sensor, compared to the desired angle, and adjusted by a controller and actuator. This closed-loop setup ensures precise movement, whether it's for a robotic arm in a factory or a mobile robot navigating a room. Mobile robots use block diagrams to map out navigation strategies. Sensors detect obstacles and position, controllers process this information, and actuators adjust the robot's movement. The feedback loop allows the robot to adapt to changing environments and reach its destination efficiently. Balance control is crucial for humanoid robots. Sensors continuously monitor the robot's orientation, and controllers make rapid adjustments to actuators to keep the robot upright. This closed-loop control is what allows robots to walk, run, or even dance without falling over. Block diagrams are widely used in automotive engineering. For example, cruise control systems use sensors to monitor speed, controllers to process the data, and actuators to adjust the throttle. This closed-loop system maintains a constant speed, even as road conditions change. Anti-lock braking systems, or ABS, are another great example. Sensors detect wheel speed, controllers process this information, and actuators modulate brake pressure. The feedback loop prevents wheel lockup, improving safety and control during sudden stops. Modern cars rely on engine management systems that use block diagrams to coordinate sensors, controllers, and actuators. These systems optimize fuel injection, ignition timing, and emissions, ensuring efficient and reliable engine performance. In aerospace engineering, block diagrams are essential for designing autopilot systems, altitude control, and satellite attitude control. These systems use sensors to gather data, controllers to process it, and actuators to make precise adjustments, ensuring safe and stable flight. Autopilot systems in aircraft use block diagrams to integrate multiple sensors, controllers, and actuators. These systems automatically adjust the plane's heading, altitude, and speed, reducing pilot workload and enhancing safety during flight. Altitude control systems use sensors to measure the aircraft's height, controllers to process this data, and actuators to adjust the control surfaces. The feedback loop ensures the plane maintains the desired altitude, even in turbulent conditions. Satellites rely on attitude control systems to maintain their orientation in space. Sensors detect the satellite's position, controllers process the information, and actuators make tiny adjustments. This closed-loop system keeps the satellite pointed in the right direction for communication and observation. Across all these fields, control systems play a vital role in ensuring safety, precision, and reliability. By using block diagrams, engineers can design systems that respond quickly to changes, maintain stability, and deliver consistent performance, whether it's in a robot, car, or aircraft. Let's bring it closer to home with a robotic vacuum. This device uses sensors to detect obstacles and map the room, a controller to plan the cleaning path, and actuators to move and adjust direction. The feedback loop allows it to adapt to furniture and keep your floors spotless. Drones use sophisticated control systems to stay stable in the air. Sensors measure orientation and speed, controllers process this data, and actuators adjust the motors. The closed-loop feedback ensures the drone can hover, fly smoothly, and respond to wind or sudden movements. In factories, industrial robots use block diagrams to maintain welding precision. Sensors monitor the welding process, controllers adjust parameters, and actuators move the welding arm. The feedback loop ensures high-quality, consistent welds even as conditions change. When analyzing a control system, it's important to identify the main components: the sensor, controller, and actuator. The sensor gathers data, the controller makes decisions, and the actuator carries out actions. Recognizing these roles helps you understand how the system works and how to troubleshoot issues. Sensors are the eyes and ears of a control system. They collect information about the environment or system state, such as position, speed, or temperature. This data is essential for the controller to make informed decisions and keep the system running smoothly. The controller is the brain of the operation. It receives data from the sensor, compares it to the desired value, and determines what actions the actuator should take. Controllers can be simple or highly complex, depending on the application and required precision. Actuators are the muscles of the system. They carry out the commands from the controller, making physical changes such as moving a robotic arm, adjusting a throttle, or steering a vehicle. Without actuators, the system wouldn't be able to interact with the real world. An open-loop system example is a basic toaster. You set the timer and the toaster heats for a fixed period regardless of the bread's color. There's no feedback to adjust the process, so the outcome can vary depending on initial conditions. A closed-loop system example is a modern thermostat. It measures the room temperature, compares it to the set point, and turns the heater on or off to maintain the desired temperature. The feedback loop ensures consistent comfort regardless of outside changes. Block diagrams use standard symbols to represent different components. Rectangles are used for system elements, circles for summing junctions, and arrows for signal flow. Understanding these symbols is key to reading and creating effective block diagrams. The summing junction is a critical part of closed-loop systems. It calculates the error by subtracting the feedback signal from the reference input. This error signal is then sent to the controller, which decides how to correct the system's behavior. Signal flow is represented by arrows in block diagrams. These arrows show the direction in which information travels from the reference input through each component to the output. Clear signal flow helps engineers trace how changes in one part affect the entire system. The error signal is the difference between the desired output and the actual output. It's what drives the controller to make adjustments. By minimizing the error signal, the system achieves its goal, whether that's maintaining speed, temperature, or position. Block diagrams are not just for professionals, they're also valuable teaching tools. By breaking down complex systems into simple blocks, students can grasp fundamental concepts more easily and build a strong foundation for advanced engineering topics. Understanding block diagrams helps bridge the gap between theory and real-world engineering. By practicing with real examples, students can see how abstract concepts are applied to solve practical problems in robotics, automotive, and aerospace industries. Now let's put your knowledge to the test. Think about everyday robotics applications like robotic vacuums or drones. Can you identify the sensor, controller, and actuator in each system? Is it open loop or closed loop? This exercise helps reinforce your understanding and prepares you for real engineering challenges. In a robotic vacuum, the sensor detects obstacles, the controller plans the path, and the actuator moves the wheels. The feedback loop allows the vacuum to adjust its route in real time, ensuring efficient cleaning even in cluttered environments. For a drone, sensors measure orientation and speed, the controller processes this data, and actuators adjust the motors. The closed-loop system allows the drone to maintain stability and respond to environmental changes, making flight safe and reliable. In industrial robots, sensors monitor the welding process, controllers adjust parameters, and actuators move the welding arm. The feedback loop ensures that each weld is precise and consistent, even as conditions change on the factory floor. When analyzing a system, look for feedback. If the output is measured and used to adjust the input, it's a closed-loop system. If not, it's open-loop. This distinction is key to understanding how the system maintains accuracy and responds to changes. Closed-loop systems offer several advantages. They can adapt to changes, correct errors, and maintain consistent performance. This makes them ideal for applications where precision and reliability are critical, such as robotics, automotive, and aerospace engineering. Designing effective control systems isn't always easy. Engineers must consider factors like sensor accuracy, actuator response time, and potential disturbances. Block diagrams help visualize these challenges and develop solutions that keep systems running smoothly. As technology advances, block diagrams will continue to play a vital role in engineering. They'll help us design smarter, more autonomous systems, from self-driving cars to intelligent robots and beyond. Mastering block diagram representation is a key skill for future engineers. To recap, block diagrams are powerful tools for representing, analyzing, and designing control systems. They simplify complex systems, enable mathematical modeling, and facilitate stability analysis. Understanding block diagrams helps you connect theory to real-world engineering applications in robotics, automotive, and aerospace fields. Congratulations on completing this overview of block diagram representation and its applications. With these foundational concepts, you're ready to dive deeper into control systems and explore more advanced engineering topics. Keep practicing with real-world examples, and you'll build the skills needed for a successful engineering career.